Hey, wonderful, good morning. 4 notions of explainable AI. Actually, it's more going to be 1 notion of explainable AI and 3 other things, but hey. Thanks for the introduction. As Maria already said, I'm from City, University of London. Since last year, we're a proud member of the University of London. We had to exchange lots of letter paper because by now the comma matters. Before that, we were City, no comma, University of London. Okay. Then, honor to whom honor is due. Most stupidities, I say, are by my own making. If there should be something intelligent in between, it's presumably due to one of these two. Derek Doran, who is an assistant professor at the Department of Computer Science at Wright State University in the somewhat godforsaken but beautiful Dayton, Ohio. And Sarah Schulz, who is a recently graduated PhD in natural language processing in Stuttgart. Also, there is a pamphlet of ours on arXiv, which summarizes most of the thoughts I'm going to force upon you over the next 19 minutes. Okay, then, quick history lesson along the lines of, basically, we already had that over coffee. Basically, everything we do is already been done in the 80s or 90s. We just revamp it currently. So let's think back to the good old days of the good old AI civil war, symbolic versus connectionist. I know we're ramping up again, but we're not yet there. One of the main arguments for the symbolic side usually was that symbolic knowledge is somewhat more comprehensible than all these statistical or connectionist techniques. I know that's up for an argument, but let's just stick with it. This was one of the majority opinions. Then, in the 1980s, a guy in the UK called either Donald Michie or Donald Michie, opinions differ, actually was around when machine learning got started proper, and he back then, quite lucidly, introduced what he called 3 criteria of machine learning. So in his definition, machine learning in its weakest form occurs whenever a system generates an updated basis building on sample data for improving its performance on subsequent data. I think everyone can agree to that. So the system does something, it gets a bit of data, and it improves over time from the data. Where it gets more interesting is the strong criterion. So a machine learning system meets the strong criterion if it fulfills the weak one, and in addition, it has the ability to communicate the internal updates in an explicit symbolic form. So you might be running a connectionist network or something like that, but there is some symbolic, explicit communication of what changed from one point in time to the other. Emphasis on some symbolic communication. And then there is what's called ultra-strong learning. And this presumably is what many of us in this room would aim for, although few will be aware of it. Here, the strong criterion has been met, so there has to be machine learning, as we understand it, there has to be communication, but additionally, the communication of the updates must be operationally effective. So the user of the system is required to understand the updates and can draw, reasoning to consequences from it. The user actually communicatively understands what happened in the system and can improve in future time steps the system-user interaction based on it. 1985, 1986, 5 notions of machine learning, or whatever the thing was called, from a European machine learning workshop. Good. Let's have a quick look at the state of play today. So, if there are any deep learners in the room, feel free to throw things at me, but what we presumably currently are witnessing is the weak machine learning empire. So very few people actually bother going for symbolic updates or even for communicatively effective symbolic updates, but what currently is predominant is a form of machine learning which on applications is highly efficient and deeply impressive. So I'm not gonna try to steal anyone's great ideas here, but nonetheless, presumably even in a very basic and very foundational sense, deep learning and most of these layered network techniques as practiced today are bound to remain weak. If your network learns a representation unguidedly, there is no intrinsic reason whatsoever why this representation might refer in its conceptual content to anything meaningfully addressable in the human perceived world. And it happens to be one of the basics of communication, that we only can talk about stuff if we both agree on the existence of the stuff. So there is a bit of a barrier here, right? Like deep networks learn representations, but we might have no clue what these representations are and whether they refer to anything meaningful for us. Serge is already nervously playing with his beard. I'm looking forward to the next coffee break. Okay, so this said, what Tarek, Sarah, and I actually did, following a call by Zach Lipton, who kicked off this entire somewhat philosophical, somewhat computer science debate in 2016, was have a look at how the words explainable, interpretable, what have you are currently used. Conclusion, it's a mess. A conclusion from the conclusion, one might want to order that in order to at least know what we all are talking about, and in order to also have a bit of a fairer basis of comparison between different systems and approaches. Okay, in this slide, what we suggested, and which has widely been ignored this far, but hey, is to introduce different system categories depending on how I don't know whether interactionable is a word in the English language, but how much they enable a user to interact. So, category 1, opaque systems. In this case, we are just talking about some AI system which for a user basically works like an oracle. You have no freaking clue what the thing is doing. You feed it input, it gives back output. The output tends to be quite helpful or accurate, but how it gets from the input to the output, like whether there is a deep layered network, whether some chickens have to be sacrificed to obscure gods, you don't know. It just works. There can be two cases where this happens. One is usual closed source proprietary AI. So if someone has an interest in protecting what the system is doing, this usually forces you to be opaque. Or if you're using a genuine black box approach. There are actually way fewer genuine black box approaches than people usually believe. But here we are talking about the real deal. For some reason, you line up some non-deterministic computation units and it always gives you the right answer. This is a proper black box. Somewhat more meaningful and somewhat more prevalent in current discussions is what we would call interpretable systems. So here we're talking about a system where the user cannot only see, but also study and understand to a certain degree the input-output mappings. For this you need a property which tends to be referred to as model transparency. So the user can actually open the lid, look under it, and see what the model does. B, this usually requires the user to have a certain level of expertise. So even if you think about the simplest examples usually brought forward here, like a regression model, I presume that for most people in this room, a regression model is interpretable. If you now take a random person on the central line at 8:30 in the morning, you show them a regression model and tell them that their life depends on it, presumably you end up in a straitjacket. So interpretability is a property of a system which might have requirements towards the user, but at least in principle, given expertise and sufficient resources, maybe a pocket calculator, maybe a couple of sheets of paper, maybe something more refined, you can, in theory, learn something about the input-output mapping. Second example are usually SVMs and linear classifiers, like everything where you get a decision boundary or where at least you have somewhat mathematically meaningfully and for abductive purposes usable output. Here, I think, is the point where deep artificial neural networks come in again as a counterexample. First of all, as I mentioned, there's this problem with the reference of the learned internal representations. Secondly, whilst possible in principle, if I give you a 60-layer deep neural network doing some fancy nonlinear transformations, I believe that with sufficient time, dedication, and caffeine, you're able to reconstruct for one single case what might have happened. But this is just not scalable. So this is a good old-fashioned tractability argument, right? Like you can do it for one if you have infinite amounts of time and stuff, virtually infinite, we know, but it just doesn't scale. Then there is, and this now ties back to good old Donald, comprehensible systems, so systems which together with their output emit some kind of symbol or action behavior. Please don't nail me on symbols actually being logical formulae being processed in minds. which allow the user to relate properties of inputs to outputs. This shifts the burden once again to the user, but differently than for interpretable systems, because here you just get these symbols and the user has to comprehend them. This can once again introduce a gradient, so some people have a bigger working memory than others, some people are just more familiar with certain contexts than others, but at least one can engineer against that, and cognitive psychologists and also usability experience researchers are quite happy to talk about less and more comprehensible representation systems interaction forms. Examples here are some inductive logic programming, inductive functional programming of statistical relational learning systems, or the currently quite popular receptive field visualizations on convolutional networks. So you have a picture classifier, which is a convolutional network. You push through the pictures, it tells you dogs from wolves, but you want to know why does it do that. So for example, LIME is one of the frameworks which, at least then in the input pictures, highlights the most significant regions determining the later classification. I'll come back to that example, keep it in mind. And who's been around in AI for long enough already will start smiling when they hear dogs and wolves. So, how do these notions relate to each other? I'm still not sure whether the picture helps or confuses, but I kind of like it. So, on the lowest level, you have opaque systems, which are just black boxes. You throw in something, out comes the truth. Good old Oracle, at least in 99.99% of cases. If not, yeah, well, statistics just hit you. Then you can try to have these systems comprehensible. So the system writes out some symbolically meaningful content. Here, for example, we are classifying pictures. You have this input picture where the system recognizes, well, there are halogen lights, there's a concrete floor, there are boxes and machines, and the label which comes back is factory. So what you as a user now have to do is you have to know, well, all of these labels are typical for things you would find in a factory, so you have to interpret the comprehensible output, and then you know, or at least you think to know, why classify it that way. Alternatively, if you will go for an interpretable system, we're talking about a white box where you have an accessible model. Presumably it shows you, well, let's make it simple, it shows you a regression over the different factors. They might even be meaningfully corresponding because you previously ran an image classifier and labeler over it. And then you know, well, it weighted the presence of a concrete floor and of boxes and machines to a high degree. It completely ignored the fact that there is some arbitrary blue things in there, but then you also can derive why it got the label factory. Still, important difference, interpretability requires model transparency. Comprehensibility can still be a completely opaque black box. It's just that the system writes out something. And you have to bona fide trust that this somewhat relates. Going for a bit of an intuition pump here, both of these systems or both of these types are actually united in doctors. If you think about what a doctor does when talking to a patient, the doctor presumably is a comprehensible model. Because, well, you do tell the patient, yeah, you know, you have high blood pressure, you're looking a bit sickly, you can't really climb stairs anymore, presumably you have a heart condition. This does not elucidate the reasoning beyond a very basic level. Like, if your doctor told you you have a heart condition only based on these three observations, either you want to change doctor, or you just believe that there is a deeper underlying reason, but this is the level you can comprehend. When talking to another medical practitioner, doctors usually tend to be much more like interpretable systems. They actually discuss medical tests. They actually just throw the real data at each other without the need to break it down or to make it comprehensible. Because, well, both of them are experts and they know how to read each other as a transparent system. So both of them are, like, both of these characteristics are there. It just depends on the context you're acting in, which is yet another important observation. So your audience and your context of action might be quite important for what you're actually building there. Okay, as you might have noticed, these were the three other concepts. Let's have a look at what we think an explainable system actually would do. If there are any philosophers in the room, apologies. I'm trying, but I'm still a computer scientist, as are most other people. So we were wondering what actually makes an explanation. Yeah, you might notice this is either a Don Quixotean or a Lewis Carroll type of question, but hey, these are fun, right? What is the standard go-to if no one has an answer? Well, at least for a second language speaker, the Oxford English Dictionary. So, an explanation is a statement or account that makes something clear, a reason or justification given for an action or belief. This is clearly completely unsatisfactory, but better than nothing. If we now compare current AI or ML against that definition, we already, for example, in the presentation of the previous speaker, saw approaches where you take a network or some opaque system and you try to write out a decision tree from it. This is good and fine, and this is clearly already more interpretable or more, well, I don't want to call it explanatory because that would confuse my own classification. This is clearly a step closer to understanding what the system does than before. Nonetheless, even these systems which produce rules about data features usually just tell you how a decision was made, not why. The difference is subtle but important. So a decision tree usually is a ex post explanation, and quite often it's even a simplification which does not match up to the original algorithm. Then there are the second type of system, like the ones I mentioned, where you visualize the significant regions, for example. So you provide visualizations or text. There you need human-driven post-processing. So if you have a look at the original line paper where they have the dogs versus the wolves, if you see the example, oddly enough, the most significant regions are white spots in the background of wolf pictures. Anyone wants to have a guess what might be white spots in the background of wolves? Exactly, the system learned to classify snow from not snow. Which works fair enough, right? Like it just happened to be the case. Or it learned presumably more, but in the visualization, this is what comes out. So there you did an interpretation step. You understood that the white stuff is snow, that snow correlates to wolves, that dogs tend to be domestic, and that in very few houses there's snow. Okay. Still, what would you do if you would have a completely scattered out highlighted range because the classification happened to be on certain pixel properties or on certain properties of the lens, if you cannot relate anything? Then comprehensibility is gone again. Zach Lipton, whom I already mentioned beforehand, who wrote a somewhat provocative position paper in 2016 on how interpretability is used in the field, basically concludes that the term interpretability holds no agreed upon meaning, and yet machine learning conferences frequently publish papers which wield the term in a quasi-mathematical way. We all know this never stopped us from nothing, but at least it should be noted. So, what we think is the big difference between being interpretable or comprehensible and between actually providing an explanation is that explanations usually are lines of reasoning which are formulated in a human understandable way using human understandable features of your point of origin, which for most automated decision systems are input data. Interpretable and comprehensible systems enable explanation because either you can have a look at the reasoning process and you can cook up your own story, or you get insight into the meaningful, if the comprehensible system works, you get insight into the meaningful parts of the story, but you still have to connect the dots yourself. So what you would have to add to that, and this is where it becomes obvious that I've been educated in the good old-fashioned AI empire, is you need reasoning. You actually need reasoning over semantically meaningful content. Because explanations, if you have a look at everyday use, are just also stories. We want to have a narrative. How could you, for example, do that? Going back to the somewhat stupid but illustrative example of the factory. Well, say you get the comprehensible system where you know it has the lights, the concrete floor, the boxes, and the machines. And, oh wonder, you happen to know an ontology engineer, and that ontology engineer built you a domain ontology over buildings and types of buildings. In this case, you take the labels, you throw it against your ontology or knowledge base, your reasoner tries to map why one might lead to the other, which is a pretty simple problem solved for all somewhat usable description logic formalisms. And it then can actually cook up a story along the lines. The image has halogen lights or concrete floor boxes and many machines. These objects are often present in and related to factory operations. The machine thus believes the image is of a factory scene. So this component here is trivialized, right? Because there you already get the labels and everything. What Tarek currently is doing in a quite impressive way is that he trains deep networks on image classification and in parallel then trains symbolic theories. So you take the actual model and in a wrapper approach, you train a description logic ontology model in parallel to match what the correct classification model does and cook up the story to it. Have a look at Tarek Doran's homepage or get in touch with him. Before concluding in about 2 minutes, a quick note on what are actually traits of explainable systems. So this is a very standard notion, which you will find in a couple of HCI papers where people claim that if your systems do not show confidence, trust, safety, ethics, and fairness, they are not legibly callable explanatory systems or explainable AI systems. What has to be noticed here is that this is always a user relative notion. So confidence and trust basically means that your user believes, trusts, confides that your system is actually truthful and that the outputs are okay. Safety, ethics, and fairness depend on, well, societal and individual standards. I don't want to go there, but these things are usually thrown around. What I'm much more fascinated and completely confused by is what people usually think makes an explanation. So now stepping out of only presenting mathematical models, but in the sense of the GDPR, or at least in the strong reading, trying to give subjects of automated decision-making meaningful insight into the logic underlying the decision, quote ends. What would we have to do? We would have to take John Smith on the street and have a system which explains to John Smith why he just lost his house because he didn't get his credit. So people are wondering, so what might be necessary for an explanation? Some people say, well, whatever quits the epistemic longing is an explanation. So whatever makes you feel you got an answer. This, I don't think, holds the test of time, because then thunder and lightning just go back to Thor hitting his anvil with a hammer. If you're a Germanic warrior at around 1000 after Christ, you're perfectly happy with that. It even allows you to act because you can sacrifice something to make Thor a little more happy. Yeah, but this is not an explanation unless you're a Freudian psychoanalyst. There it's helpful. So, quitting the epistemic longing presumably is necessary but not sufficient. Then, some people say explanations should be truthful. If you're a metaphysical scholar, this might be desirable. It's also pretty good because then you can put explanations directly next to numbers in Platonic heaven. Nonetheless, if you have a look at how explanations actually work in the real world, truthful enough is probably the better phrasing. Rutherford Bohr atom model, the atom works like the solar system, is complete bollocks. We know it's wrong. Still, it's helpful for most people in daily life and especially in physics and chemistry class in school. It's an approximation to truth. It's clearly wrong, but it does the trick. And it's, I think, a fair explanation. And then there are the people who say an explanation should be complete. No, just no. You do not want to have the complete explanation from your doctor. In very different scenarios, either because if your doctor explains to you a metabolic pathway, this is not at all helpful. If the doctor just tells you, well, please eat a little less red meat and you will stop being yellow, that is fair enough, because this will just reduce the bilirubin levels. If you are diagnosed with a lethal disease, it might also just be mercy on the side of your doctor, not to give you the full account, but just to spare you. But all of these are explanations in the common sense how used by people in the street. I know that I'm conflating real world and our tech world, but the already mentioned GDPR and some of the other explainable AI initiatives might make that necessary. I don't have a single answer to any of that. Don't get me wrong, right? But these should be noted. What are better desiderata? No idea. I'm currently arguing with a scholastic logician over that, but this argument might not conclude anytime soon. Summarizing, I introduced Opaque, Interpretable, Comprehensible, and Explainable Systems as a categorization, and we of course happily invite you to use the same in your work, create a bit more clarity, and boost our citation scores on Google Scholar. It has to be noted that interpretability and comprehensibility are different. Interpretability presumably are white box systems. Comprehensible systems can perfectly be black boxes as long as they are communicating. Both of these approaches lack in the capability to reason and to actually provide complete narratives. We think that explanation necessarily requires reasoning. It doesn't have to be of the symbolic type, right? Like no paradigmatic claims whatsoever. But there has to be reasoning. Here's the reference. And last 5 seconds, quick advertisement. If by any chance you should be interested in explainable AI, there is a special interest group on explainable AI within the Neurosymbolic Learning and Reasoning Association. You can visit the website. We have set up a mailing list a couple of weeks ago, which by now has some 300 registered people. We hope to use that for announcements of papers, events, what have you, and for the occasional hangout at a bigger conference where you want to geek out even after the official program ends. Thank you.
Thank you, Tarek. Good talk.